Hello, this is Mrs. Schroeder, and we are back in chemistry talking about how to write net ionic equations. This is showing you how to do equations with solubility rules from double displacement reactions, how to write total ionic equations for anything that occurs in an aqueous solution, and being able to identify spectator ions in the solution. Because what we don't want is this unwanted precipitate. If you were a chemist and you were doing something in the environment, you would not want to have this nasty yellowish orangey stuff in your streams. You want to make sure you don't have unwanted precipitates happening. Aqueous reactions are anything that occurs in water. When you have an ionic compound in water, it will dissolve. It'll actually break into its individual ions. So Ki dissolves and forms K and I ions. They're separate now. We've broken those bonds holding them together. Same thing with lead. If I actually were to be able to peer inside of a beaker that had these things, I would actually see the individual ions floating around in that solution. And I could see the Pb and the NO3 floating around in the solution. And if you look at the ratios, there's 2 NO3s. There's more NO3s in this solution than there are lead ions because there's 2 of them for every 1 Pb. So we do see that if we peer inside of the solution, we would see those individual ions floating around. In a double displacement reaction, we said it only takes place if you actually form a precipitate, a gas, or a liquid. If I just poured those last 2 beakers together and no reaction happened, it would just be a mixture of those ions. The beaker would be a little more full, and you'd have all the ions from here in here too, but if I don't have anything happening, it's just a new mixture. So I need something to happen, either a precipitate, a gas, or liquid. So how do I know if a precipitate will form? I have to use my solubility rules. These are guidelines you can follow to determine if an ionic compound is soluble, which means it dissolves in water, or insoluble, which means it does not dissolve in water, or it will turn into a solid in water. A precipitate is the insoluble compound that forms when you pour those 2 things together. If it forms an insoluble compound, we use the symbol S, which indicates solid. So I will use the solubility rules to tell if the double displacement reaction will take place. And here's some rules. You don't need to write these down because I will give you a handout in class which has these on it, along with your activity series of the metals. So, but in general, if I look at these, compounds of group 1 and NH4 are soluble. So that tells me that anything that I see that has a group 1 element, sodium, lithium, potassium, rubidium, any of those things would be soluble. I can look at anything with nitrates or acetates are soluble. And again, it assumes that you know that a nitrate is NO3 minus and an acetate is C2H3O2 minus. Again, reasons why you had to memorize those earlier in the year. A halide is any halogen. Again, a halogen is group 17. So assuming you remember all of those things, those terms, if you don't, talk to me and we'll make sure you understand what they're supposed to be. So what I want to do is be able to use our solubility rules to figure out if compounds are soluble or not. If I look at the first compound, Na2CO3, and I want to say, is it soluble or not? Well, I'll go back to my rules. Na2 is a group 1 compound. Therefore, I don't have to go any further. I say it is soluble. Okay. The next one, copper nitrate. Okay, well, copper is not group 1, so that one does not apply. But it is a nitrate. All nitrates are soluble. Therefore, copper nitrate is soluble. Alright, the next one, calcium sulfate. So I go to my rules. It is not group 1. Calcium is in group 2. They're not nitrates or acetates. They're not halogens. It's a sulfate. All sulfates are soluble except with calcium. So if it says all sulfates are soluble with the exception means it's insoluble. Okay, so we'll go through more of these in class to practice them. Soluble compounds will dissolve into ions when we put them in water. So what we're talking about is, the earlier slide I said I have PbNO3, 2. When I put that in water, I form the ions, the lead ion and the nitrate ion. Going back to other one, Na2CO3. If I put that in water, Na2CO3. Well, what's going to happen? Na breaks up into its ions. Its ion is Na+. There are 2 of them. So I don't leave the 2 as a subscript because it's not Na2 bonded together. The 2 implies bonding as a subscript. The 2 in front says how many you have. And then I have the CO3, the carbonate ion, is a 2-. I need to include the charges and include the numbers of them if they have a subscript. Reactions that take place in water, we can describe them by showing how the ions take place. 2 terms you'll need to know: total ionic and net ionic. Total shows all of the ions, and net ionic shows only the ones that change. So net are ones that change. Total is everything that is in the solution, the beaker. Example, the Ki and Pb. I had those 2 beakers. I showed you the first slide. I pour them together. Okay, so I have Ki and my Pb. Pour them together. My solubility rules tell me this: PbI2 is a solid. If I want to write the total ionic equation, I would need to write them as the pieces of the solution to show all of the ions that have happened. Ki turns into this. The 2 of them goes with each one. There's 2K and 2I. The lead nitrate turns into right here. When it reacts, it forms the lead 2 and the NO3. The lead iodide, you'll notice, is still a solid. It did not break up. Solids are not, if they're insoluble, they're not broken up as ions in the reaction. And the 2K plus and 2NO3 from the potassium nitrate. Now if I look and say the ions that remain unchanged, this term is called spectator ions. So the ones that remain unchanged are like spectators in the sport. They're there, but they don't really participate. So I look to see which ones are the same, which are unchanged, the same on both sides. Potassium is the same on both sides. That's a spectator ion. My iodine changed. My lead changed. The nitrate is the same on both sides. So NO3 minus is a spectator ion. Now my net ionic equation, I'm going to show only the ions that changed. So I don't show the spectators. I cross them out. And I rewrite it with just the ions and the solid that formed. So that would be your net ionic equation. One quick example we're going to show you is the zinc. It doesn't have to be double displacement. It can be things like zinc, which is a solid, and copper is a solid. So if I write this out as the total ionic equation, zinc is a solid. It remains solid. Copper is aqueous. It has a +2 charge. Sulfur, or sulfate ion, has a 2- charge, and it's also aqueous. You do need to show the state of all of them. It turns into copper solid. There's no charge because it's a solid material, has no charge. The only time I show charges is if I have an aqueous solution. And my SO4 2-, is aqueous. This would be the total ionic equation. If I look at the net ionic equation, I want to find the things that don't change. So first I have to identify the spectator. So if I look at this equation, spectator ions are things that are the same on both sides. SO4 and SO4. So SO for the sulfate ion is the spectator ion. In this case, I only have one. It's a single replacement reaction. So the net ionic equation shows that zinc solid plus copper aqueous turns into copper solid plus, I think this is supposed to be zinc. I don't know why my zinc changed to nickel. So turns into zinc 2 plus. And this is aqueous. So this would be a net ionic equation. So we will do some more of these examples in class tomorrow. In general, remember how you do these. Total includes all. Spectator ions are the ones that are the same on both sides. And net is what is left, or what changes over the reaction time. Solubility rules, again, we'll practice using those. I have a handout for you, so don't worry about writing all those things down.